about maybe 7:15. So yeah, everything's really, really smooth, and if y'all need help, I'll probably be able to do this.
Okay.
So that's not funny.
As long as we get the sound fixed, I think we should be fine.
Okay. I hear audio. You're fine.
I don't have anything. Is it me? Is it somehow me? Shouldn't be.
I hear audio on the live stream, so.
You do?
I'm so confused.
Yeah. Audio's fine.
Okay, I don't know what's up with my computer, but here we are.
That could have been it. If you paired your Bluetooth headphones with after you were pairing, if that way you might still be using the transmitters or something.
Courtney, can you hear me?
Yes.
Okay. Why am I still here twice? I am not then hearing myself on the stream, so I think I can talk to you. Oh, wait, never mind. There's this really long lag.
Hi everyone. We're so happy to have you here. Welcome to our first show of the year. This time, hopefully, we have less technical problems. We're very happy to have you all here, and we're excited to have a new year ahead of us. As you've clearly noticed, we're still online for the foreseeable future, and our current plan is to follow CDC guidelines on when it's safe to return to an in-person show. For now, we're using this as a really great opportunity to give you non-local speakers without having to bring them all the way down to Baton Rouge. So we hope you enjoy at least that part of it. Before we get started formally, I'll mention just a few things. We haven't had any issues yet, but I just want to be sure, so be considerate in the chat. Feel free to drop your questions at any point during either of the talks, and I'll field them to the speaker at the end of each talk. As always, feel free to donate to our Venmo and PayPal. It helps us keep the show alive. And in the message of that donation, let us know what you think of this month's tip war. This month, we're asking you if you think that the new SETI radio signal observations from Proxima Centauri were from aliens or just from a microwave. For some context, in about mid-December, the Breakthrough Listen project from SETI, the Search for Extraterrestrial Intelligence, reported they had detected radio emissions from the closest star system to us, Proxima Centauri. It's only about 4.2 light years away. The implications of this observation aren't yet confirmed, but we want to know what you guys think. Do you think it's aliens, or do you think it's just another microwave like that old fast radio burst thing? The last thing I want to mention is please like this video if you're watching and subscribe to our YouTube channel so that we can get a unique YouTube link. That would be awesome. Now on to our talks for today. Our first speaker tonight is currently a professor at Ohio State University, so sorry about his national championship game. He got his PhD from the University of Florida and has a passion for long-distance running. His astronomy research focuses on planets outside of our solar system, and today he's going to tell us about how we can use the study of exoplanets to help us answer the age-old question, are we alone in the universe? So it's my pleasure to go ahead and introduce Dr. Ji Wang. Ji, if you'd like to share your screen and get going, we can get all that started for you.
All right, I'm going to share my screen. All right. All right, and can everyone see my screen here?
You're all good. Good to go.
All right. Awesome. Good. Just want to check my marker here. Good. All right, the marker is good. Okay, so today I would like to talk about searching for an alternative life. So when I try to decide the title of this talk, I Google this talk, but what I find is instead of astronomy related topic is more search result, return result for like meditation on how you change your mood, things like that. So, but anyway, I stick to this topic, stick to this title, searching for alternative life. And in a few minutes, you're going to understand what I mean by alternative life. So a bit background for myself. I was born in Guilin, China. It's a beautiful city. I encourage you to Google the city and at some point to visit the city by yourself to appreciate the natural scenery of this beautiful city. And I got my bachelor from University of Science and Technology of China and then received my PhD at the University of Florida. And then I moved on to Yale University where I overlapped with one of the professors at the LSU, Tabby Boyajian, and we became best buddy. And then I went to California as another term of postdoc before I get my professorship at the Ohio State University, where I overlapped with another LSU faculty, Matthew Penny. So this is pretty much my personal background. And before I get to today's main topic, I would like to ask everybody a question. What is in the air, in the Earth atmosphere? Like, what do you think the composition is? If you can put in a chat or shout out anything, any way you feel comfortable, just treat it as a little survey. All right. No response. Normally I would get.
Am I allowed?
Yeah, sure. Everyone is welcome.
Well, I'm gonna guess nitrogen.
Nitrogen.
One. And oxygen.
That's a good one. Oxygen. Yeah, those are the two major constituents in Earth atmosphere, right? Nitrogen and oxygen. In fact, they consist about 98% of Earth atmosphere. However, today I would like to bring you to your attention another molecule's contents in the Earth atmosphere, in addition to oxygen, which is methane. Okay, and I want to stress the importance of the coexistence of oxygen and methane, and what does it mean when it comes to searching for life on another planet. So the reason I want to mention these two molecules is because of this chemical reaction, right? Both methane and oxygen are highly reactive, like they're reactive with each other and they turn into carbon dioxide and water, right? So the fact that they are so reactive, meaning that you either find one of the two. You don't normally see the two coexist, right? If the two coexist in the atmosphere, that means both of which have been replenished in some form. So that's why I want to introduce two concepts, the source and the sink, right? The source is something that is continuously producing a certain molecules. And the sink is something that is continuously consume the source. So in the case of the Earth atmosphere, the methane is the source and the oxygen is the sink. And the fact that we continuously see the two, meaning that there are something continuously producing these two molecules, right? It's obvious that we know that forests continuously provide the oxygen. But what is actually continuously producing the methane? Everybody's welcome. No guess?
The cows. Is it the cows?
Bingo. So we have cows that continuously producing methane. Even though methane is continuously being consumed or reacted with oxygen, we have cows continue producing it. So methane actually is the biosignature of Earth, and the coexistence of methane and oxygen is highly indicative of life for Earth-like planet, right? This is what we are going for. So we are hopeful that one day we can find oxygen and the methane in Earth 2.0, meaning that another Earth-like planet, just like our Earth, right? Or in other words, Earth analog, right? The way we find methane and oxygen is through their spectral features. If you disperse the light of an Earth-like planet, and hopefully then you will find oxygen, which is usually in the ultraviolet wavelengths and the visible light. And you can find the methane, which is usually around a few microns in the near infrared. Okay, so if you find the sink and the source all together, that is quite a powerful message that we get from another planet that cried out that Earth life is here. So come to us. So before we get to too Earth-centric, right, we have to ask ourselves, is Earth-like planet the most common type of planet in the universe or in the Milky Way, right? Are we being too narrowly focused in searching for life? When it comes to life, shall we be more open-minded and think about other type of planet? So here comes the other question I want to answer in this talk. Are Earth 2.0 common? And if they're common, are they the most common type of planet, right? Is it our best bet in search for life? The answer is not quite. And if you look at the Kepler result that gives you the occurrence rate, how common the planet of different size are, this Earth-like planet is not as common as super-Earth planet and the mini-Neptune. Super-Earth and the mini-Neptunes are only a few times, 2 or 3 more times bigger than the Earth-like planet. And they appear to be the most common type of exoplanet. So the next question becomes, instead of focusing on Earth-like planet and searching for biosignatures, should we shift our focus on those most common type of exoplanet in the Milky Way? Right? What is their biosignatures? What is the biosignature for super-Earths and mini-Neptunes? What are the source and the sink? So before we answer this question, we have to get to know a little bit more about the super-Earth and a mini-Neptune. What is the real difference between a super-Earth and an Earth-like planet? The biggest difference lies in the atmosphere composition. Right? The atmosphere of a super-Earth or mini-Neptune is mainly dominated by hydrogen and helium. Right? The reason is easy. Think about the hydrogen or helium balloon that you have. Right? It will fly away from Earth because the Earth's gravity is not strong enough to hold on to hydrogen and helium. In comparison, super-Earths and mini-Neptunes are massive enough to hold on hydrogen and helium. The gravity is so strong that they are able to hold on hydrogen and helium such that their atmosphere is dominated by hydrogen. And one of the consequences of a hydrogen-dominated atmosphere is that everything will react to hydrogen first. Yeah, think about the Earth atmosphere. Everything will react to oxygen first, right? But this is not the case for super-Earth. Everything reacts with hydrogen because this is hydrogen is the most dominated species. Okay, so for example, oxygen reacts with hydrogen to become water. Carbon reacts to hydrogen to become methane, and the nitrogen, as shown here, react with hydrogen to become ammonia. Right? Why do I want to show this chemical reaction equation? First of all, this equation, chemical reaction, produced heat. Okay, heat is very, very essential to keep any life, right? Because we rely on a certain chemical reaction to provide the heat for our metabolism. So this action produced the heat. And the second of all, this reaction doesn't go one way or the other. It actually depends on the temperature and the pressure. Only when the temperature is very high, like hotter than 1880 Fahrenheit, in order to synthesize or to combine nitrogen and hydrogen into ammonia. Okay, so it doesn't happen in a condition where you expect life, right? This type of temperature here is too hot for liquid water, for which we thought is essential for life. And under what condition could this reaction go from left to right, right? Because in our case, if we want to think about a very habitable environment, for example, 80 Fahrenheit, right? I'm not sure the temperature in Baton Rouge. I mean, here it's definitely colder in Ohio, but temperature 80 Fahrenheit is very common on Earth. And can we expect such a chemical reaction go from left to right? Right? The answer is probably. Why? So imagine, just use your widest imagination. Think about a life that has an enzyme, like a catalyst, to catalyze this chemical reaction, such that under temperature condition at 80 degrees Fahrenheit, nitrogen and hydrogen can be synthesized into ammonia to produce the heat to be harnessed by life, which possessed a catalyst, an enzyme, to facilitate this chemical reaction. So this is what we want. Okay, this is what we imagine. And in fact, there have been quite a series of papers hypothesizing that life on a super-Earth could use this chemical reaction to get the heat. And also they possess that kind of enzyme to facilitate this chemical reaction at a low temperature. right? So if that is the case, now we find the source and the sink for super Earth-like planet, for super Earth planet, right? Just to remind you, the source and the sink for Earth is methane and oxygen. And the source of a super Earth is ammonia and the water, right? Ammonia, despite a very low concentration, will immediately be dissolved in the water, as it is the case on Earth or everywhere. However, if there is something keep producing ammonia, right? If you always maintain a level of ammonia in the atmosphere such that we can detect it. As a result, the simultaneous detection of ammonia and the water is a signal to us that super Earth possessed life that has the enzyme to synthesize hydrogen and nitrogen into ammonia so that we can detect it. Okay, so if you use this analogy, and I hope that you are convinced that ammonia and water are what we are going after for super Earth. So this all sounds like a wildest dream, right? However, it's not that far away in the future. Because if you could imagine this ammonia world, and we know where to search for the ammonia feature, right? This is one of the a paper that my student Caprice Phillips and I are writing together, try to convey this message to show people that ammonia is within reach with the next generation of space telescope. So where do we go to search for ammonia? We go around this 10 micron. 10 micron here is basically the thickness of your hair, right? The wavelength of 10 micron is where we have this abundant absorption signal from ammonia, even at a very, very low concentration. Even at this low concentration level, which is about 1 part per million, that we can still detect ammonia because it's such a strong absorber in the atmosphere. So if you wonder, like, how do you translate this concentration of ammonia in the atmosphere to the biomass? Right? The answer is that this about 1 part per million concentration of ammonia correspond to about 1 gram per centimeter square biomass. Okay, so in comparison, the Earth has about 10 gram per centimeter square. So even at the biomass that is 10 times less massive than that of Earth, we can still detect the ammonia that is produced by this imaginary life on super Earth. So this is a quite sensitive method. And the Caprice is doing a lot of simulation, try to prove that one day after the next generation telescope, James Webb Space Telescope, which is scheduled to be launched in 2021, which is this year in October, right? Hopefully by the time this telescope flies, and we can use it to search for the ammonia, which is the biosignature of super Earth. And hopefully before we can claim victory in detecting oxygen and methane, we can claim the victory in detecting ammonia and the water on super Earth. And that's an alternative way of detecting life. And that is the reason why I chose the topic, searching for alternative life. Okay. And that, I think that's it for my talk. You're welcome to ask any questions or any comment. Go ahead.
All right. Okay. So if you want to stop sharing your screen, we can transition to the Q&A. And since there is just a slight delay from us talking to each other and the stream itself, I'm going to start with a few questions for myself. And since, you know, our biggest asset at AOT is our speakers, I'm going to ask you a few questions about yourself, if that's all right.
Sure.
What would you say a normal day of work looks like for you, whether it be in these times where you're potentially working at home or like an actual normal day?
So a normal day for me, first of all, I work from home. But my daughter still goes to school, so I have to drop her at a preschool and I come back to work. Normally I would drop her at school around 9:30 and come back to work until 4:30. In the middle, I will work continuously, and then I will take 1 hour off to do exercise. And at 4:30 is my pumpkin time. I have to go to school, pick her up. And then I will spend time cooking dinner, play games, and I will send her bed at 8:30. And now today is my wife helps out so that I can give this astro tap presentation. And there goes the day, and then keep repeating. And on Saturday and Sunday, we'll try to do something differently. But at this time, there's not too much to do, given that we're stuck in COVID, stuck in Ohio.
So you said you spent some time like playing games. Do you mean playing games with your kid, or do you play like actual, like your own single games?
No, just with my kid.
Okay.
I'm not a big fan of like cyber game or computer game.
You know, the demographics tend to overlap a lot, so I just thought I would ask. What percentage of time would you say like your actual work is like spent at a telescope, just to give people an idea of how much like astronomers are actually at telescopes?
So sadly, nowadays as the technology gets more and more advanced, we don't have to be at the telescope in person. Most of our proposed observation will be done remotely, not even by us, by observer, because at OSU, we have access to the Large Binocular Telescope that is located at Arizona. So they hired telescope operator and observers, and we put in our request and they put in a queue. So they will basically observe for us, and the data will flow to our hard disk in amount of time, usually within a week or so. So I would say it is not as fun as the time, because I have been, in both. I've been in both before the transition and after the transition. So I know what it's like to go to telescope, observe, stay up at night, and reduce the data, publish the paper. So it's a very fulfilling experience. However, I feel like nowadays that part of getting the data, the excitement of hoping for good weather, hitting keys to operating telescope, that excitement is gone. So I really feel most of the time I feel very reminiscent of old days where I can go to telescope and stay up at night.
And then potentially break the telescope. That's a common astronomer story.
There's no way you can break. I mean, maybe there is a way of breaking telescope, but it takes a lot of effort to do so, because there are a lot of safety measures to prevent careless and sleep-deprived astronomers to break telescope.
Yeah. Okay, so I'll start fielding you some questions from the actual chat on our YouTube stream. The first is a bit of background stuff from Stephen Dorsher. He asks, can you just remind him what an enzyme is chemically? It's a special kind of catalyst that belongs to biology or organic chemistry, or can you explain that?
Yeah. So enzyme, it's a jargon. I mean, I don't know how to use the layman's word, because you can either call it enzyme or catalyst, depending on where your background is. But pretty much is I teach life in universe. I usually use this analogy. So it's like a sofa, right? Like a two-seat sofa, right? It's there, it's sitting there, but you usually have person A and a B. They sit in a sofa and they react to each other. And when they leave, instead of A and B, they become C and a D, right? The sofa is just a place where a chemical, enzyme is a place where a chemical reaction takes place. And a chemical reaction can only take place there, or maybe it's easier for chemical reaction to take place with the facilitation of enzyme. So you can think about it as a, catalyst is a pretty layman word, right? Catalyst.
Okay. And then a second question that he had was, do we know what the sources and sinks are for super Neptune-like planets? Does anyone search for life on those kind of planets?
In my terminology, super Earth and mini Neptune are of the same category. Both of them are heavier enough or massive enough to hold on to hydrogen and the helium. So their chemical composition, the atmosphere chemical composition, is very similar. The difference is that the mini Neptune has a thicker atmosphere than super Earth. So the gravity, surface gravity, or the pressure is higher in mini Neptune. Sometimes you may expect false positive. Like by false positive, I mean you may expect ammonia to be produced abiotically in mini Neptune simply because of high pressure. Abiotically meaning not in a biotic way, right? So, and I also want to mention the production of ammonia has been done in factory for at least 100 years. So they use catalyst, but in this case, in the case on Earth, it's not a life that is catalyzed the reaction. It is like iron. They use iron as a catalyst to facilitate the synthesis of hydrogen and nitrogen. And this chemical reaction takes place at about 450 degrees with a very, very high pressure. So that's why I say in a mini Neptune, if the pressure is high enough, then ammonia could be produced by a way that is not associated with life in any way.
Okay. We have another question from a friend of AOT, Andy. I'm sorry, Andy, I don't know your last name. But he asks, what would be the most common kind of life form if it wasn't carbon-based? In your opinion?
Silicon.
Silicon?
Yes. So this is also another topic that I mentioned in my Life in Universe class. So people usually ask, instead of a carbon-based, what could be the alternative? Silicon is most similar to carbon in terms of chemical properties. The difficulties of forming silicon-based life are at least twofold. First is that silicon is not as versatile as carbon, meaning that it doesn't form millions of organic molecules, right? Silicon can form like simple chain, simple cycle, or simple form, but it doesn't kind of connect you to very long chain as carbon does, right? Our protein is a long chain of carbon that connects to each other, but silicon doesn't have that property. So any life, if at all, formed from silicon will be very simple. And the second difficulty would be silicon is not dissolved in water, right? So that means, maybe silicon life doesn't really require water. It may require something different that a silicon life could be dissolved in. Because having a solvent for life is critical. Just like water could help us to, for example, provide an environment to provide an environment where high concentration of chemical could be there to react with each other. And water could carry away the waste and bring in the energy, right? So water or any solvent is essential. So silicon life is facing those two difficulties, in my opinion. So it's less likely, but who knows, right? Life threw a lot of curveball to us.
Okay.
Life.
Yeah. We have two more. First one is from Collins Hurley, who's now a professor at LSU. To what degree do you think the presence of super Earths is due to them being more common compared to them being easier to detect? And does that affect searches for biosignatures?
Yes, so I think super Earth is indeed more intrinsically more common than Earth-like planet, and all the occurrence rate that I show in one of my previous slides are corrected for detection bias. And indeed, I think Colin, right?
Yeah.
Colin? Colin has a good point that super Earth is easier to be detected because it's more massive, it's bigger. So therefore, that's why we want to pick super Earth as a prime target for the search of biosignature. Because we know that if there is a biosignature in super Earth, it is at least a factor of a few easier to be detected than Earth-like planet, simply because of the size and the radius disparity between these two types of planets. To give you some example, I just want to make,
Good.
Super Earth is usually twice as big as Earth, right? So think about the time it takes to observe a super Earth than observing an Earth. If it's twice bigger for super Earth, then the telescope time is 4 times shorter, right? So instead of 40-hour JWST time, now it only takes 10-hour JWST time, which seems to be more manageable, right? So instead of asking for a Porsche, now we only ask for a Toyota Prius. So it's easier to get a telescope time that way.
And then our last, but not actually last question is from Jonas. I think that's Jonas in the chat. Can you make an educated guess where we might find life first, i.e. what kind of stars or within the solar system?
Within the solar system?
Yeah, like which
within or
is more
outside?
likely.
Okay, yeah, there's always a debate, right? The race of finding life elsewhere, is it within our solar system or is it in an exoplanet?
Yeah.
So in our solar system, there are 4 most promising places to find life: Europa, Enceladus, Mars, and most recently, Venus. Right? Venus may be a fluke, but I include that in anyway. So, I'll leave it to planetary scientists because I don't want to get in the debate with a planetary scientist. But outside, I think planets around M stars are pretty cool, although there are a lot of adversities for life for planets around the M stars, like flares, tidal locking, right? But, life is pretty resilient. We should have hope for planets, for life on planets around the M stars. So I'm open-minded person, so I will pick planets around M stars.
Okay. And then our last question, he didn't ask, but I'm going to ask for him anyways, from Tabby's son, Jude. And he always asks what speaker's favorite Pokemon is.
Pokemon? He asked the wrong person because neither me or my daughter are interested in Pokemon. If I ask my favorite Paw Patrol, I can give you an answer, but I don't play Pokemon.
All right, that's a 1 for Pikachu then. That's a 1 for
yeah,
Pikachu,
I know Pikachu, and I only know Pikachu. So
yeah, well, there's a reason for that. Okay, so we're going to go ahead and break to intermission. Before we actually do that, I'd like to humbly ask everyone to consider donating to our Venmo and PayPal again, and then just remind you to let us know your answer to this month's tip war in the comment itself. So while we take a quick break, we'll be presenting you with some fun space trivia so that you can impress your friends. And we will be back at 7:41, which is a weird time, but it's okay. So we will see you all back here then. And go ahead and give G a thanks in the chat for yourself. Alrighty. And then we'll go to intermission.
All right. Thank you, Courtney.
No problem. I believe
is that all? Should I?
By the way.
Okay. So I gotta mute myself and stop the video then.
Yes.
Countdown again.
Alrighty, welcome back, everyone. Thanks for sticking around with us. We're going to go ahead and get started with our second speaker and skip all that fun extra stuff since I've said it a million times now. But our second speaker today is a new postdoctoral researcher here at LSU. He did his PhD project at Heidelberg University in Germany, where he studied microlensing, which he's going to tell us a bit about today. So I'm happy to introduce you to a man who was, in fact, crazy enough to move to the US during a pandemic, and that is Dr. Jonas Kluter. So if he wants to start sharing his screen and get going, here we go. Don't forget to unmute.
So yeah, here I'm sharing the screen. So yeah, so I like to talk about astrometric microlensing and how we can use Einstein's relativity theory of relativity to determine stellar masses. So let me ask first a question. What is the mass of a sun? And as an astrophysicist, this answer is quite simple. It's one solar mass. However, this is about 333,000 times the mass of the Earth, and about 1.99 times 10 to the 30 kilograms. And another question is, how do we know that? And the mass of the sun was measured for the first time back in 1668, or something like that, when the guy on the left-hand side, Isaac Newton, used the equation from the guy on the right-hand side, Johannes Kepler, to determine the mass of the sun. And yeah, so at that time, he didn't know what the gravitational constant he just invented or discovered was, so he derived the mass of the sun in units of the mass of the Earth, and he determined a mass of 169,000 Earth masses. And if you remember the last slide, this is roughly by a factor of 2, which is mainly due to the poorly known distance of the sun at that time. So, and a little bit fun fact about Isaac Newton: when he developed his theory of gravitation, he was in home office due to a plague pandemic back in Cambridge at that time. So the same method as Newton used to determine the mass of the sun can nowadays be used to determine the mass of a binary system. However, not every star is in a binary system, and we might also be interested in the mass of an individual star. So how do we determine the mass of an individual star? And here on the right-hand side, you can see a so-called Hertzsprung-Russell diagram, which is similar to a color magnitude diagram. So we have on the x-axis the temperature of the star, which can be translated into a color. And on the y-axis, we have the luminosity, which can be translated into the magnitude or brightness of a star. And you might know that there are different kinds of stars. So we have the so-called main sequence stars, which going here along this line. And we have giant stars or supergiants, and we have white dwarfs. And for stars on the main sequence, it's possible to determine the mass using the so-called mass-luminosity relations. And there are some other relations which can be used, like the mass-radius relation. However, the mass-luminosity relation is the most popular one. So if we have a star down here at the bottom, so it's about 1% of the mass of the sun, and it's going up to 60 solar masses here at the top. However, this equation can not be used for white dwarfs or for giants. And it is not derived theoretically, it's derived by observations. So it's calibrated on binary stars, where we can determine the mass rather simple. And there's the evolution of a star also is strongly dependent with the mass. So, for example, if we have the lifetime of a star, we have found that a star of a solar mass of about 10 solar mass of a mass of 10 solar masses has a lifetime of about 10 to the 7 years. And if we go to the red dwarfs or brown dwarfs, the lifetime of a star can easily be longer than the time of the universe. The universe exists. So, however, what we also know is from theory is that single stars evolve different than binary stars. So it is not known how well the relations we determined based on binary stars fits to single stars. So it's really important to directly determine the mass of an individual star. And to do so, there are only a few methods. So one is astroseismology, where we observe variations in the brightness of a star, and from that determine different variations. And there's astrometric microlensing. So what is astrometric microlensing? 100 years and something years back, Albert Einstein said that light gets attracted by gravity. And so if we have a star, there's a certain in a certain direction, we will see it on the sky. However, if there's another star in between, the light from the star is blocked. But there's also light which will not go directly towards the Earth or to us as an observer. And this will bend it due to the theory of Einstein's theory of relativity. This will cause that we will assume that the star is at a different position. So instead of the position here, we will see the star down there. And in fact, there's also the possibility that this light is passing on the other side of the foreground star, so we might see a second star on the other side. So this picture is true for gravitational lensing in general. And depending on what kind of source we have and what is the type of mass in between, it's called either strong lensing or weak lensing or microlensing. And For microlensing, the main difference is that this lens and the sources are typically stars in the Milky Way and they are in motion. So if you remember my first slide, you saw a glass of wine. And the idea of this glass of wine is to simulate microlensing or gravitational lens. So if you take the glass of wine and hold it roughly like that, be sure that the glass is empty. What you would see roughly reflects to the gravitational lens. And yeah. So, and that's what you're seeing here. So in the background source, you see an image of Orion, and when the lens or the wine glass is passing by, you can really see that the position of the stars are shifted a little bit. And if you have a closer look, especially on those stars here, you will also see that there are two images of that star. And so what you also can see from that image is that stars closer to the center of the glass of wine are deflected stronger than glasses at the edge. And so it scales with the inverse of the separation. And it also scales with the so-called Einstein radius. So the Einstein radius can be interpreted as the size of the wine glass. And yeah, so here I have another animation now with the exact equations. So what you will see in a second is that the lens, so the foreground star, which is indicated by this green line and with its Einstein radius, will pass by a background star. And due to the astrometric microlensing, we will see these two images. So there's a light one and a brighter one. So when it passes by, the background star will make a small little circle and will also be distorted. And the size of the two images are reflecting also the brightness of the star. And what you can see is that when the star is passing by, the red image gets much larger, and also the blue image will become larger. So there are two different kinds of microlensing. So with the brightness difference is called photometric microlensing, and this can be used to detect exoplanets. And the top one is the astrometric microlensing. And if we go to another impact parameter, so another distance between the lens and the source, we will see that the photometric signal is nearly gone, but there's still an visible astrometric signal. And so the size of the signal, on the one hand, depends on the impact parameter, or this angular separation, and on the size of the Einstein radius. And it's only a really small effect. So it's in the order of milliarc seconds. So 1 milliarc second is roughly the size of a person laying on the moon. So it's a really small amount which we deflect. This background star will be deflected. However, with the best telescopes, we can observe these effects, even if they are so small. The effect will only occur for stars which are close by, and therefore these events are extremely rare. And I will come to that at the end of my talk. However, we cannot have longer time scales of the events, so we can observe such events over a few years, and we can predict those events. And finally, when we measure the deflection, this is directly proportional to the mass of the lens. So this event, or astrometric microlensing, was observed for the first time back in 1919. And at that time, the theory of general relativity was rather new, and the British astronomer Arthur Eddington tried to observe this effect, which was predicted by Einstein, during a solar eclipse. And by comparing these observations with observations done in half a year earlier, he measured that the stars are indeed deflected, are indeed further away from the sun during a solar eclipse. So, and from that he calculated that Einstein's prediction was correctly. The alternative was that Newton's theory of relativity or Newton's theory of gravitation was also valid for massless particle, but it turns out not. And Einstein became really famous with these observations. And a funny fact, back in 1919, there was the Spanish influenza pandemic. And after these observations, it took about 100 years to observe astrometric microlensing, also for a star, except for another star. So we're in 2013, 2015, Sau et al. Measured the light deflection for the white dwarf Stein 2051b. So that's this star, when it passed by a background source. And indeed, they managed to measure the deflection, and from that deflection, they were able to determine the mass for Stein 2051b. And there's, on the same way, a few years later, they measured the deflection for Proxima Centauri. And currently there are several proposals and observations going on. So how can we use now astrometric microlensing to measure stellar masses? The first question which needs to be answered is, when and where on the sky will such an event happen? And this I have done in one part of my PhD thesis. So I used the data from the Gaia satellite, which is an astrometric satellite, and measured the motion and positions of thousands of stars. And from forecasting their paths, I was able to find astrometric microlensing events or predicted astrometric microlensing events. As for Newton, who had to know the distance of the sun, we also have to know the distance of the star. And fortunately, we can use the Gaia parallaxes for that. So the parallaxes is a measure for the inverse distance. And the last step is to observe these events. And by comparing the observed position with the calculated unlength position, it's possible to derive the mass. And so what we found, or what I found, is that there are about 60 good events in the next per year. So I searched until the 50 years in the future, so probably the end of my scientific career. And there are about 2 promising events per year. And for one of those, we wrote recently a JWST proposal. Then there's another one just before, shortly before 2020, which we are currently observing. And there is this Gaia satellite, which is on the sky until mid-2024. And in the second part of my PhD thesis, I showed that for the stars or for the events happened before or happened during the Gaia mission, a rather good mass determination is possible by Gaia itself. So we get those roughly for free and might only need a few additional observations. Yeah, so what are the conclusions? So first of all, pandemics are a really good time to measure the mass of the sun in a new way. Albert Einstein was right when he predicted astrometric microlensing. And astrometric microlensing is a unique tool and a really good tool to use for measuring stellar masses. So thanks.
All right, great talk. If you want to unshare your screen, then we can get started with some Q&A. So same rules go for you. I'm going to let some of the questions fill up in the chat, and I'm going to ask you a few questions in the meantime. But I wanted to start with a few things. I wasn't sure if you were looking at the chat while your talk was going on. I think that would be really hard. But a lot of people were very impressed by your wine glass video and had never seen anything like that. And it really is a good way to sort of explain that. Also, this is the first time a few of us realized there was actually an astrometric counterpart to microlensing events. So definitely taught me something today.
Yes, so the astrometric counterpart, which was observed first, but then only forgotten because we don't have the instruments to do so. So it's whether new or part of the effect, or it's well known, but not so often observed. It's really hard to observe. So we cannot use only the big telescopes. So that's why photometric microlensing is more popular, because it's easier to do.
Speaking of popular, did you follow this year's Exo Cup? Are you familiar with that?
No.
So on Twitter, there's like every year they do an exoplanet like cup thing where you vote on your favorite exoplanets and they have like brackets and stuff. Anyways, this year's finalist was two planets that I actually don't remember, but I remember one of them was a microlensing planet. So I wasn't sure if you had heard about that or if you were excited about it.
Yeah, so to be fair, from astrometric microlensing, it's really hard to find exoplanets. So I wasn't in the exoplanet fields. I
just wasn't sure if they sort of work the same way. I don't know. But
do and there or when photometric microlensing has really advantages in finding exoplanets. So especially those who are far away from the or have large separation to its host star, and also this discussion of free floating planets also.
So just a few questions about yourself. What got you into like astronomy as a person? Like, what would you say was your first experience, or what made you really excited about it?
Okay, so back in high school, I wanted to become an architect, and then I started to study physics. And and I went into astrophysics, mainly due to the lecture about exoplanets from my professor in Heidelberg, where I then wrote my bachelor thesis about the astrometric microlensing events of Proxima Centauri, and now my PhD thesis. So that's why I moved into astrophysics, and I got mainly interesting in doing the data analysis, and so that fascinated me, and is a nice way to use these tools. Yeah.
All right. What's something that you wish people knew about astronomers or astronomy in general? Sorry, that's kind of a hard question. I'm sorry.
Yeah, so most important was the difference between astronomy and astrology.
That's always a good one, you know?
Yeah, it's so it's
just that one is fine too. Have you ever heard that old adage of like, if you're on a plane and you're sitting next to someone you don't know and they ask you what you do, you go through this mini checklist in your head. It's like, do I say astronomer? Then they'll ask me what their horoscope is. Do I say physicist? Because then they'll be like, wow.
So when I'm talking to people and told them what I'm doing, most of the question, that's I wouldn't can. Or the most popular answer is, I cannot do that. It's for me. So, and that's why I like this analogy of the wine glass, because it's easy to use. You can have a wine glass on every party, so it's a nice way to tell them what you're doing and why it's interesting, and then the other one gets interested in that. So, I would say I'm doing astrophysics and try to rate a star.
Alrighty. So our first question from the live chat is from Stephen Dorsher. He asks, do they see an astrometric wobble in the star in addition to the star's wobble in its orbit around the center of mass when they do exoplanet microlensing?
So, when they're doing astrometric exoplanet microlensing.
Either way, a binary star would work too. If there's a wall.
So for a binary star, it's really easy. So you can see them because what we can see in the data is the parallax effect. So we can see that there's a slightly different effect due to the Earth's parallax. So if we can consider that there is another star like Jupiter around the background about that star, there's also a small variation. However, it's typically below the resolution of our telescopes. But there might be a shift also if there is a photometric microlensing effect, mainly because the background source gets brightened, and so we have an asymmetric shift due to that we observe the star at, have another contrast between the lens and the source star, which is more dominant.
Okay. In your talk itself, you mentioned or like alluded to that astrometric microlensing is predictable. How do you predict the microlensing events?
So, the astrometric microlensing is predictable. So we are using the position of the stars and the of a foreground star. So we select a certain list of potential lenses and looking for stars behind that or close to that lens star. And by calculate or using the measured proper motions and positions, we then forecast their path. And then just searching for close encounters. So this is possible for astrometric microlensing because the accuracy of the data is good enough for the resolution we need. For photometric microlensing, we need encounters which have the size of the Einstein radius, which is only a few milliarc seconds. And so the data are not good enough to predict those events with high confidence. So
I see. That makes sense. And then these don't repeat, right? So they're not repeating events. Does that negatively affect the science that you do with it, or does it not really affect it?
Yeah, so they are once in a lifetime events. So if you missed one, you missed it. So when the second Gaia data release was published in 2018, and I first started the search, we found one really interesting event which happened at that time, which we tried to observe. And due to technical reasons, the observations failed. So we tried to use the gravity instrument at the VLT or VLTI, which is a really complex instrument. So it's really tricky to do so. And so there was another event, or there is another event of the same star, which is currently going on. However, due to this stupid pandemic, the observatory closed down. So we lost that for the, yeah.
But I thought you said that pandemics were perfect for observing.
And only for the sun, no.
Yeah. You gotta add in that caveat.
But so I used the pandemic to write a PhD thesis, which is, I believe, totally fine.
And then a few more science questions. Do you think they'll ever detect solar mass or intermediate mass black holes in binaries or moving nearby using photometric or astrometric lensing?
So there is a study by another guy on solar mass black holes, and they might be detectable within the Gaia data set when they have a typical mass of 30 to 40 solar masses. So not one solar mass, but 30 to 40 solar masses might be detectable in the data. However, the data will be published in 2024-ish, 25-ish. So it will need some time so until we can do that because of some badly rules within the Gaia consortium. So you're not allowed to do science with the data until they are published.
Right.
It is totally fair, but so I have to wait until that.
Emily asks, M dwarfs are the most common stars in a galaxy, so they tend to be the most common microlensing stars, right? Do you have estimates for M dwarf masses? And if yes, how big are the error bars?
So the for binaries, we can determine the mass of a M12 with an accuracy of a few percent, or even better if they are in some cases. And with microlensing, so for the event of Stein 2051b, the accuracy is 6%, and for Proxima Centauri, it's 30 to 40. It's sometimes really challenging because we have to observe the background star, and typically the foreground star is much brighter, so we have to come over the contrast problem. But with microlensing, it's possible to reach an accuracy of a few percent as well.
Yeah. LaDonna McKnight asks, what would be the best location on Earth to observe this type of event? A microlensing event, I'm assuming.
Or on the Earth, the position on the Earth isn't really important. So what I'm doing is mainly space, using space telescopes, so Gaia, JWST, or HST. So JWST in the future, or what is coming up after JWST or so. And you are limited to the big telescopes. So, and therefore the observatory are mainly shielded. So.
All right, and I hope you were preparing for this last very important question from Jude. What is your favorite Pokemon?
Yeah, my favorite Pokemon is Gyarados, I don't know what's the pronunciation is because or the names of the Pokemons are translated into German. So.
Yeah. No, you're good. Gyarados. Gyarados is a good one. Definitely a good one. All right. So I think that is our last question. Thank you, Jonas, for a very good talk. I know G has already left, but he had a very good talk as well. So thank both of you for volunteering to come and talk with us. We know you're busy with all of your work and stuff, but we're very, very thankful to have you and also G give us a talk today. I also want to give a shout out to our streamers, Ali, Alex, and Benjamin, who were behind the scenes today, working really hard to put the show on for us with significantly less technical difficulties than last time. So that is a success. Before we head out, just a few things I'll mention again. I'm humbly asking you again to consider donating to our Venmo and PayPal. And if you're watching us asynchronously and not live, feel free to still interact with our video. It does help us out. Leave a comment, like the video, reach out to our social media, what have you, anything that you feel comfortable doing. Subscribe to our channel as well so you can get notifications for our next show when our show is going to go live, and help us reach 100 subscribers so that we can get a unique YouTube link. That would be super awesome. So keep an eye on our Facebook, Instagram, and Twitter, where we'll post about all of our events as soon as we know about them. And we'll see you here on YouTube next month, where we'll have 2 more lovely speakers. Until then, I'm going to Muppet wave, as I am contractually obligated to.